Hi everyone, in this video we're going to be talking about some of the dicarbonyl chemistry that you've been learning in class. So let's begin. So dicarbonyl is, of course, as the name suggests, any molecules that have two carbonyl groups, right? But these are the special classes where not just any dicarbonyl, but 1,3-dicarbonyl. So if you start numbering, it's 1, 2, 3. So these are special in the sense that you have this alpha carbon to the carbonyl that is alpha to both of them. Okay, this alpha position is alpha to both of them, right? And as you know, both of the carbonyl groups are electron withdrawing group. Okay, so if you have two electron withdrawing group next to these alpha proton, it makes them super acidic. So as you will know, these have pKa's in the range of probably 9 to 10, as compared to a single carbonyl, which has pKa 10 to the 10 times that, or like 10 unit greater. Okay, so what's special about it is because they have because they're super acidic, you could use a weaker base to deprotonate these. For example, you could use sodium methoxide. Okay, it's important to know that you should match your base, whether it be ethoxide or methoxide. Make sure this matches whatever the ester it came from. Okay, I'll explain that more in my session. Okay, so if you use that, what you're going to get is you're going to form the enolates, right? Okay, so after you form the enolate, right, you want to do chemistry with it. So the most common chemistry is doing alkylation, enolate alkylation, right? So let's say you add this one, right? So what's going to happen is going to push the arrows and you're going to alkylate this, right? So these are alkylated beta ketoesters or alkylated dicarbonyl. Okay. So since there is again another proton left, you could perform the alkylation again, or you could stop here and do decarboxylation, which is what you're going to see a lot this quarter. Okay. So to do decarboxylation, you need an acid, HX, right? Usually it's an aqueous acid, so there's water in there, and heat. So what happens is the water and acid will hydrolyze. Okay, so you hydrolyze to make carboxylic acid. Nothing happens to the alpha group. But what the heat does, as I showed in the previous video, it decarboxylates, right? So it takes off from the carboxylic acid, so just erase it, okay? So your product will look like this, right? So if you know what you've just done is essentially you did a net alpha alkylation, right? But you did it through a different mechanism, like decarboxylation. Before, you had like a ketone, acetone, right? You'd use LDA and then ethyl iodide, right? To get to the same product, right? So the goal of using these dicarbonyls compound to start with is it allows you to do the alkylation and essentially reach the same product, right? Eventually reach the same product, essentially reach the same product without using a very strong base. If you noticed here, you need an LDA because it's a single carbonyl compound. It's not as acidic as the dicarbonyls. Because it's not as acidic, you need to use a stronger base to perform alkylation. So this is essentially, the top method is an alternative method where you're technically doing the same chemistry, but but you're using a weaker base. Okay. The reason being is LDA wasn't really invented to, like, I forget when exactly, but 1950s, maybe 60s. So anytime before that, when chemists needed to alkylate an alpha carbonyl, right, they didn't have a strong base available to them. As a result, what they ended up doing is they picked carbonyl compounds which were super acidic, typically dicarbonyl. They alkylated it, and then they decarboxylated it to get these alpha alkylated product. Okay, and I'll explain more in my session.